thank them for putting on. I think this is a fantastic event. I've enjoyed it. I've been here now for almost a week, and I'll be here until tomorrow. So I'll give another lecture tomorrow. Today I'm going to focus on particle acceleration and the basics, and then tomorrow I'll try to apply this more towards radiation and making connections with a lot of the things that Alicia spoke about yesterday, and we'll talk a bit about later today. So I noticed that about half of you are working on particularly high energy astrophysics related to particle acceleration and neutrinos. So a lot of the concepts here will probably be familiar to you, but hopefully you can still glean something useful, maybe a new perspective on some of the topics. And for those of you doing gravitational waves, hopefully you'll extract something useful when you look for electromagnetic signatures from these events. Okay. Just say what I hope to get across today, key learning outcomes. So to get an idea for the essentials for non-thermal particle acceleration in astrophysical systems, how to generate spectra, and what is the maximum energy that you can achieve at a particular source. These are always the two questions we're always asking ourselves with any given source, because we're always looking to understand. And the key measurements are basically the shape of the spectrum of the particle or the radiation spectrum, and how you infer from that the particle spectrum, underlying particle spectrum, and the maximum energy that you can achieve, because this is a nice clear radiative signature and is also directly connected to many of the open problems in high energy astrophysics. So a warning, as Martin did yesterday, there is some assumed knowledge, but really basics of electromag, bit of special relativity and hydrodynamics, and there'll be some fairly light mathematics. So I've tried to gloss over anything that's too complicated, but there is a few very simple essentials, which equations will be absolutely are unavoidable. Okay, so I'm going to break up today's talk essentially into 5 different subsections. So listed here: non-thermal emission from astrophysical systems, sort of introduction and motivation. Again, there'll be a lot of overlap with what Alicia was talking about yesterday. And so then some basic essentials of particle acceleration, so introducing key concepts and some absolute truths. Before moving into de facto acceleration mechanisms. So this is the pioneering work of Enrico Fermi, who really set the foundation for this in his dying years. And then introduce what is let's say, my favorite acceleration mechanism, which I think accounts for the vast majority of observations where there are very high energies, basically particle acceleration at shocks. And then I'll have to do a little digression into my favorite topic, which is plasma physics. So my background is in plasma physics, and underlying all of the interaction between particles and magnetic fields is basically plasma processes. And so these start to play an important role when we really want to understand the maximum energies and other possible radiative signatures. Okay, so why do we want to study this at all? And so one of the main motivations, and you will hear this again and again, this is cosmic rays, right? The simple fact is that cosmic rays exist. And my colleague, Tony Bell, would always say, if I didn't know any better, I would say these shouldn't exist, but they do. Okay, and so we want to understand where they come from, how they're produced, and it's quite a remarkable spectrum covering, more than 10 decades in energy, with a rather featureless spectrum, which is certainly not Maxwellian. It's not a thermal distribution. Okay, they arrive at Earth almost isotropically to about 1 part in 10 to the 3. And we don't know for certain where they come from. We do know quite a lot experimentally from the measurements. So we know the energy density. So their energy density about 1 eV per cubic centimeter. This is, for example, comparable to the energy density in the magnetic field in the galactic disk, also thermal motions. So it's a major player in galaxy evolution. Okay? Cosmic rays in general. From composition measurements, we know we can do a little bit of detective work, and we can infer simple things like the mean residence time in the galaxy for where the bulk of the energy is sitting. This is the order 10 to 100 million years. We can similarly work out a mean free path. And so the mean free path as a function of energy is roughly about a parsec at a GeV, and then increasing. The exact scaling of this, current experiments would suggest it's about a third. Could be slightly larger. But the key thing is that this is the mean free path. So this is the distance over which a particle more or less forgets where it's coming from. So unless the sources are all within 1 parsec, which they're not, then there's no way of inferring directly from particles arriving at Earth where they came from. The luminosity, you can now work out if we have all the information we need. If we assume that this energy density is typical, this lifetime is then also typical, and then we take the volume of the galaxy, including its halo, and then we end up with a luminosity, the amount of power basically being spit out in cosmic rays from our galaxy is about 10 to the 40 ergs per second. So it's yes. Right. So if you imagine tracing these particles from, take a point source of particles and release them, and then if they're all more or less following, let's say, initially ballistic trajectories within 1 mean free path, they've effectively randomized the direction in which they're propagating. And so everything is, sorry? No, they're scattering. This is a key point. They're scattering on turbulent magnetic field fluctuations. So they're doing effectively a random walk in the magnetic field. So there's no binary collisions. The, I'll explain a little bit about this, but the binary collision time between individual particles is the age of the universe, or longer. Okay. And then one other obvious fact is when you get up to these sort of energies, as Alicia was saying yesterday, the gyro radius, this is basically its motion in the magnetic field of the galactic disk, is larger than the scale height of the galaxy. So these are all extragalactic, certainly at the highest energies. Okay, so how do we find out where they come from? If we can't say from direct measure or local measurements, at least at the lowest energies. So we use the fact that they're primarily hadronic. So they're primarily protons, nuclei, range of other nuclei, and about 10 to the minus 3, a very tiny fraction of electrons. So if we want to find where the source is, this is where the gamma ray astronomy really comes into play. Because as these particles, although they're not colliding with one another, they're not collisional, they're not thermalized, they do every so often collide with the ambient gas in the galactic disk, say, or near sources. So in a PP interaction, so a collision between a proton, as Lisa had a nice movie yesterday, you can produce various pions, and the neutral pions specifically decay into gamma rays and some other products. For the neutrino people, of course, you all know that the charged pions will decay and produce neutrinos. So the key point here is that the gamma rays that are produced in this chain, so the parent proton, energetic proton, produces a pion. The pion decays into a gamma ray. The gamma ray will carry away approximately 10% of the energy of the initial proton. So if we have a tera electron volt proton, it will be producing gamma rays at about 100 GeV. Okay, so it's a direct signature. If we want to really look at these energetic particles, we're looking at gamma rays. This process, of course, is not particularly efficient, and this is where it makes it quite challenging, because the rate at which this process is happening is very, very slow. 10 to the 7 years divided by the gas density. So for typical interstellar medium gas densities of about 1 particle per cubic centimeter is a very, very long time. And of course, the emission is competing with much more efficient processes from electrons like inverse Compton and Bremsstrahlung. Okay, so we need to do quite a bit of detective work to figure out where these cosmic rays are coming from. And of course, observations make a major part of this. So multi-messenger, again, neutrinos and gamma rays are essential part of this story. Okay, so if we want to look for these sources, here's a list of my favorite sources. One of the thing that I spent a long time working on is supernova remnants. Here on the left, we have what was, and let's say, most of the supernova remnants that have been detected in gamma rays, and you see the spectrum here. The thing that you want to note here is that you're getting a cutoff basically at a few tens of tera electron volts, which suggests that particles are being accelerated up to about 100 tera-electron volts, so the underlying particle spectrum. So this cutoff happens here at the most extreme, and then older remnants seem to have cutoffs at sort of lower energies. More extreme environments, again, one of my other favorite sources, are pulsar and nebula. Here we have a powerful pulsar. This is the Crab Nebula, drives a wind, and then the nebula is very bright right across the electromagnetic spectrum. And so we hear this most recent data of the highest energy. So we have X-ray, this is synchrotron emission extending up to almost above a GeV, and then this inverse Compton component takes over and produces photons up to peta-electron volt photons. That's individual photons with an energy of more than 10 to the 15 electron volts, which is really remarkable. This is really at the extreme of what any system can do. Okay? And then for the highest energy cosmic rays in the universe, one possible candidate is active galactic nuclei. So here is the Auger map, and here we see Cen seeming fairly bright. And then we see the same object here, you see in the optical in this background image, and then overlaid is the gamma ray emission that we see from TV gamma ray emission from Centaurus A. Okay, so there's a clearly close connection between all of these particles, these sources, and the gamma ray emission. Okay, so statement of the obvious: to produce high energy photons and neutrinos, we need high energy particles. And the question we want to ask is, how does nature do this? Okay, so before really diving into the astrophysics, we can ask some very simple, just physical questions. Okay, so the air in the relating to your question a second ago, the air around you here, we know more or less its density. Temperature is just about 300 Kelvin. Room temperature. Mean time between binary collisions in the air around you is about a nanosecond, right? So the air is constantly bouncing off one another, and this naturally relaxes the system towards a Maxwell-Boltzmann distribution. So the Maxwellian distribution is quite standard for a collisional gas. So we can define this, or we can describe this in terms of classical collective processes or collective properties like temperature and pressure, density, etc. If we take now the interstellar medium, so density is much less, the temperature is slightly higher, and then not the mean time between collisions, but rather the time to really equilibrate can be on the order of about a year. And if you take something like the inner region of a supernova remnant, which can be 100 keV or 10 keV, 100 keV, this becomes thousands and thousands of years. Okay, so on time scales that are very much less than the equilibration time, if you perturb the system, there's no reason for it to relax to a Maxwellian. Okay, it's not going to relax back to a simple thermal distribution, and so non-thermal distributions are quite common in astrophysics. Okay, but the question is one thing to be non-thermal, right? To be out of equilibrium. It's another thing to have a small fraction of very greedy little particles taking a huge portion of the energy, right? So astrophysical plasmas tend to be completely plutocratic, where the highest energy particles take more than their fair share of the wealth of energy. Okay, so how do we accelerate particles? So let's ignore gravity, assume a flat space-time, and ignore collisions. Okay, so the equations of motion are the Lorentz force, and of course the particle velocity, and here momentum. This is gamma mv, where gamma is the Lorentz factor of the individual particle. Okay, so if we want to understand how particles are accelerated, we need to just simply solve these two equations, but of course we need to know what E and B are. Okay, the first thing to note, and many people seem to forget this very simple fact, that if we take the dot product of this equation with momentum, momentum is always parallel to the velocity, and therefore this term vanishes. Okay, and so we can now, using the fact that E equals gamma mc squared is p squared c squared, we can rearrange this equation to show that the rate of change of the energy of a particle is just the work done by the field. So you probably have come across this before, but the key point is that only electric fields can change the energy of a particle. Magnetic fields do not change the energy of a particle. Okay, and so the maximum energy that you can realistically expect to produce in any system is simply the potential drop across the system. You take the world line of the particle aligned with the electric field, and that determines your maximum energy. Okay, so what kind of electric fields might we expect in the astrophysical systems? Because this determines how high an energy you can get. Okay, well, I thought it was appropriate, since as you're making your trip to the synchrotron this weekend. How do synchrotrons do it, right? Synchrotrons produce very high energy electrons, or proton synchrotrons. They produce very high energies. And they do this by using radio frequency linear accelerators. So you charge up some capacitors, they set up a space charge field, these little gaps in between the capacitors, and they resonate. So they're always pointing to the right as this proton, I guess, is moving across. And so they just gain energy, gain energy. And this is how basically the physics underlying, or the technique underlying, most modern particle accelerators. Can you do the same thing in astrophysics? Well, gaps do actually appear in various astrophysical sources. For example, in the magnetospheres of various compact objects. You have these regions where the fields are not properly screened, and you can generate large linear electric fields over these regions, which can preferentially accelerate one species going this way, another species going this way, and this is believed to play a key part in the generation of jets from astrophysical objects. Other places where this can occur, so gaps can be produced, again, as I said, magnetospheres of pulsars and black holes, but also in rotating fields around pulsars. So you have strongly magnetized object rotating very rapidly. Its motional field will produce a large electric field. At oblique shocks, you can also produce large fields, and current sheets, which related to magnetic reconnection. These can also have large-scale electric fields. The key thing to remember, of course, is though that regular electric fields accelerate all particles in more or less the same way. This is why synchrotrons tend to produce beams at a fixed energy. That's why they work. And so without basically extending up to the system side, slow some radiation reaction, and if we ignore possible cascade effects, the outcome is that you tend to produce basically monoenergetic distributions. And so these types of processes, why they don't produce thermal distributions without some sort of collision process, they can produce, are unlikely to produce power laws. Okay, so let's not look at regular electric fields, but take more realistic astrophysical environments. So here is a simulation done by Mr. Mayron here. And this is MHD turbulence. And the thing I wanted to impress upon you here is all the multi-scale structure. Right? So this is the temperature plot, but you can see features on almost every scale within this figure. This is more typical of what we think is going to be happening in the interstellar medium. It's going to be highly turbulent, and therefore the electric fields are also not going to be very regular, but are going to be completely chaotic. The typical on astrophysical scales, we can always define the electric field via an ideal MHD Ohm's law, which takes this form here, where we only care about U cross B. Okay, so the cross product of the velocity and so this is the fluid velocity field, and this is the magnetic field. Okay, so in astrophysical plasmas, these are typically high Reynolds numbers and highly turbulent, and so U is basically quite chaotic. The reason you see all this structure is because the velocity field is highly chaotic, mixing around, and therefore the electric field and the magnetic field are going to be or the magnetic field can have a regular component, but certainly the electric field will be highly chaotic. And so here's my little cartoon. And there's an if here, if a particle can somehow decouple from the bulk of the plasma, it effectively can sample all of these different velocity fields, and therefore they see different electric fields and do more or less a random walk in energy space. And this is what was effectively the underlying principle of Fermi acceleration, which I'll explain a bit more presently. So if we now ask ourselves, how effective is this? So we saw in the case of our gaps or our linear accelerators, a particle starts off with some energy and is accelerated in a linear fashion. What's going to happen in this case? And again, this I think is the original motivation for this. Is related to your question again about being thermalizing. I thought an appropriate analogy being here in Brazil. So imagine you had that particle that I drew that was just whizzing around here. It's colliding off all of these structures here, um, associated with large scale motions. So this could be a wave packet of alphane waves or something equivalent, or individual clouds. And all that will happen is as these individual particles are bouncing off these various structures as they move around with some velocity u, they'll try to come into thermal equilibrium with those large macroscopic structures. And a very simple um, estimate. So you can imagine Ronaldinho, lots of Ronaldinhos kicking footballs around. Um, they're going to be moving around with an energy of about tens of joules. That's 10 to the 20 electron volts. And so if a particle was able to come into thermal equilibrium with all of Ronaldinho's footballs, it's already higher than the highest energy particles that we measure. Okay. The thing is, of course, I said it will try to come into thermal equilibrium with these macroscopic bodies moving around, but it will fail. And it fails because, again, we come back to this equation here. The maximum energy is simply the work done by the electric field. And the electric field, we can say, is roughly exploiting the fact that the electric field is U cross B. We put that in here for E. And we take ds to be more or less the system size. And so the maximum energy that you can ever get in some system of a finite size is roughly this. Okay, and if we just plug in some numerical numbers, let's say we take a kiloparsec, so a very large distance, typical interstellar magnetic field value, typical velocity, this is the sound speed in the ISM, and we get about 10 to the 14 electron volts. So this is a good rule of thumb. And this actually, this expression here, the maximum energy, this is a well-known result. This is called the Hillis limit. Okay. So it's also useful to consider how particles are transported in magnetized plasmas. This plays a key role in understanding how particles are moving around in the galaxy and also for acceleration. So just quickly to explain, astrophysical plasmas we think are typically magnetized. So what does it mean to be magnetized? It means that a particle is doing the lowest order helical motion. Okay, so I've drawn, here's a little simple numerical simulation, just integrating those equations that I showed you before. Okay, so with no electric field. Okay, in order for a particle to be magnetized or to do this helical motion, we require two things. One is a large scale, relatively smooth magnetic field. So take the extreme case here of a constant magnetic field just along the x-axis, and that the gyro frequency, which is the rate at which it's doing these gyrations, is much greater than the scattering rate. Okay, and again, the scattering rate is not scattering from binary collisions, but scattering on little wiggles in the magnetic field. Okay, just to explain what these terms are. So this is just our Lorentz force, ignoring the electric field. If there's no electric field, the energy is a constant of motion, and therefore we can just take the gamma m from the P down here, and we see that there's always an acceleration that's always perpendicular to the instantaneous velocity, which will always keep a centrifugal force. So this allows us to define a gyro frequency, which is effectively just the magnitude of this number here. It has to have units of 1 over time. So that's QB over gamma MC, and an associated radius, which will basically be the perpendicular velocity divided by this frequency. And then we can define a useful quantity. People have literally written textbooks on how to work out this little number h here. I'm just going to leave it as a free variable because it basically will give us everything we need to know for today's lecture. So I define this scattering frequency, which is just gyro frequency is this number h, which is called the Hall parameter, times the scattering frequency. Okay, so this figure here, there was no scattering. Okay, so h was infinity. It's basically nu scatter is infinite, or sorry, 0. If I add a little bit of scattering, all right, so I've set this h to be 1,000. So the scattering frequency is 1,000 of the gyro frequency. And I see what happens here now. The particle was, no scattering, was free to propagate along the magnetic field. The particle that has a little bit of scattering has a little bit more difficulty. It's kind of going through a little bit of treacle. Can't get as far. and it deviates a tiny bit from its initial guiding center position, the same axis. If I increase this now, or reduce rather, increase the scattering, reduce the Hall parameter, I start to see that very different behavior happens. I start to wander off from this magnetic field, and I don't get near as far. And I can extend this to make H smaller and smaller. And as long as it's greater than 1, I would still say it's magnetized. But for particle acceleration theory, we will eventually try to push this to the extreme, basically setting this parameter H equal to 1. And so the final thing that I wanted to introduce, just so we're all on the same page. So when typically dealing with large ensembles of particles, or physical kinetics, it's better to work with the distribution function. And so we generally work with the 6-dimensional quantity called phase space density, which describes the full everything you need to know about a particle. So if I take a small volume, let's say the air in my hand, yeah, I know exactly all the particles are between some x, basically some small 3-dimensional volume, everything inside my hand, so between x and x plus dx, y and y plus dy, z and z plus dz. But there's also a distribution of particles within my hand, particles moving with a large different momenta. And so I also need to be able to describe how their momentum is as well, so all the degrees of freedom. And so mathematically we do this via this distribution function, f function x, so it's a function which depends on 6 variables plus time. It basically says it's the physical number, so it's an actual quantity, number of particles within some value and within some phase space value. And so because these astrophysical plasmas are highly turbulent, I believe that those scatterings are very, very frequent, like I showed you on the previous slide, and this will always drive the system towards isotropy. So while this f is a function of the vector momentum, collisions will always drive it towards some isotropic distribution where it only depends on the magnitude of the momentum. And this greatly simplifies most of the calculations that will follow. And this allows us also to introduce something which is effectively a differential number density. So rather than being a full phase space density, it only depends on the magnitude. So it's the number of particles between p and p plus dp in the magnitude. Okay, so I can summarize the key take-home points if you haven't followed all of the equations and what was happening there. So key points: only electric field can do work on a particle. Magnetic fields do not accelerate particles; they merely deflect them. Electric field vanish in the local fluid frame. This is generally you might think is a problem for particle acceleration, but it's not when you consider that stuff is moving around. The theoretical limit for the maximum energy is what's known as the Hillis limit. Again, it's the maximum potential across the source, and can be very conveniently written as the gyro radius is some fraction u over c times the system size. So very often you'll see in many and very famous physicists make this mistake. They will say the maximum energy is when RG is equal to the size of the system. That's not true. The velocity of the scatterers is important, so it's actually a tiny fraction of the system size. So astrophysical particles are typically magnetized, and to lowest order will follow the magnetic fields. And the particles undergo regular scattering on magnetic fluctuations, and therefore it's approximately isotropic. And that, as we see, will keep things relatively manageable. Okay, so all those details, keep them in mind. Okay, and so now we jump into greater minds than my own, one of the great icons of the 20th century physics, Enrico Fermi. And this was the work that he actually spent, I think, had he not died, he would have basically advanced this field because it was the topic that he was most passionate about near the end of his life. And so the idea was the following. So really diving into the details now, we imagine we have this magnetic field. Okay, so this is the ISM, the interstellar medium. It's threaded by, as far as he was concerned, perfectly regular magnetic field. They didn't really know so much about magnetic field turbulence in those days. And imagine there was a cloud moving, right? So they did know that there was these high velocity clouds. And so Fermi's idea was to ask the very simple question, as I had already said: what happens when something small and fast hits something big and heavy? You know? Okay, so we have some velocity is much greater than, so a particle which has initially some very high velocity, much greater than the average value of some clouds. And as we said, if it's able to sample many of these clouds, it will try to come into thermal equilibrium with these clouds. But the question, of course, is how. And so Fermi gave a way to show how that works. Okay, so we can ask ourselves, what happens when we have this particle? It hits off this cloud, but the cloud itself can have quite a turbulent medium or has some sort of field structure inside it. And what Fermi was doing was played the game was that in the external medium, the electric field vanishes in the local frame. So this particle's energy is exactly conserved as it moves along. Then you do a Lorentz, or you can do a Galilean or a Lorentz transformation into the frame of the cloud. Okay, so we'll do a simple 1D picture here. So if it's the particle is going this way, the cloud is going this way, you see that the momentum in the frame of the cloud would be slightly increased. Then in the frame of the cloud, there's no electric field. In the local frame, there's no electric field. So its energy is conserved in the cloud, gets turned around, and it comes back out. And you do a transformation back into the frame of the interstellar medium, and the net effect is, in fact, that the energy has increased by a factor of 2u over v. Okay, so you get one, just think of something, billiard ball hitting off a moving wall. So if this collision was head-on, then it has a net increase in energy. It's a very small fraction, so a small increase in energy. But of course, if the cloud was moving the other way, it would have lost a little bit of energy. I would have done the same game, transform into the frame, turn it around, and it would have lost it. Okay, so we have this plus or minus here, depending on whether you're overtaking or head-on. Okay, so the idea is very, very simple. Okay, so let's extend this now to multiple clouds. So I have this particle that's doing ping pong off all these moving clouds. And so here I say I would have had a gained energy. Here I would have lost energy, gained energy, gained energy, gained energy, lost energy, lost energy. Okay. And so the question is, does this average out to zero, or do I get a systematic energy gain? And what Fermi showed is that you do get a systematic energy gain. Okay, so we know again our fractional energy change per interaction. Now, if we take the mean distance between the clouds, is some L, so it's the average over a large ensemble of clouds. And then the fact that the clouds are moving. Okay, so if L is the mean distance between clouds, the rate at which you're crossing these depends on whether the clouds are converging or moving away, right? So if the cloud is coming towards you, you cross that distance slightly less time than, which is a slightly greater rate, than if the cloud is moving away from you. You have to catch up with it. And so the net effect is that the average rate of gaining energy is the rate at which you have head-on collisions, gain energy, minus the rate at which you have overtaken collisions, and you lose energy. And so the leading order term cancels out, but these terms add up. And so what you end up is with the total energy gain that you get after a large number of collisions is a systematic energy gain in the momentum. It's always increasing. Okay. And so if we take the relativistic limit, set v equal to c, and then we see that we have the average rate is basically some constant, more or less, times the momentum. Okay, so we have a simple way of producing or accelerating particles in principle at the high energies, which is what we knew would happen anyway. These particles are going to try to come into thermal equilibrium with the clouds. Okay, so then the question is, does it produce power laws? And so Fermi threw his mind at this, and the answer is maybe, but it's probably unlikely. So we can do a simple little bit of mathematics without doing anything complicated. So we know the average rate at which you're gaining energy. So the PdT alpha p, where alpha is order u over v squared. This is a key thing. This is why it's called second order Fermi. The probability of escape, so we have to introduce an escape probability. So we take some finite region where this is happening, and there's a finite probability of which you're going to leave the system, where you no longer stop interacting with the clouds in some time delta t. So we say this is delta t over t escape. And then we can just do the following. We say that the number of particles above some momentum, p plus delta p, is simply those that have not escaped, so this is the probability that they have not escaped, 1 minus p escape, times the number at p. Yeah? So n is the total number of particles above some momentum. And so we can just do a simple Taylor expansion on this. Delta p is much less than p. It's a small increase. And what you're left with is a simple differential equation, which we don't even really need to solve, because we can just rearrange it as a log equals something. Right? And we all know that if you have a power law, you plot it in log space, and it's a nice straight line. And so the question is, does this produce something that's a straight line? The answer would be yes, if, so alpha is a constant, yeah, but t escape mightn't necessarily be. So if t escape has no dependence on momentum or energy, then you can produce a power law. This is probably not likely. Particles of different energies are going to be interacting slightly differently with the clouds and escaping from the system. So this requires a certain amount of fine-tuning. The other possibility is that this escape time is effectively infinite, and then you would produce basically a flat spectrum, or p to the minus 1. But of course, the system isn't ever going to have an infinite escape time. Okay, so so again, our key takeaway points from the Fermi's analysis. So he established a mechanism to energize particles, but again, a key point is that they need to be energetic already to participate in the first place. These days, we refer to any mechanism where particles are accelerated by sampling the relative motion of fluids. We refer to this as Fermi acceleration. So this is what a Fermi acceleration process is. The average energy change averaged over some collisions scales as the square of the velocity, and so we call this a second order Fermi process. And power laws are in principle possible, but require some fine tuning. Okay? And so just to point out that modern approaches no longer work with clouds, but work with MHD turbulence, but the conclusions are basically the same. Okay. So what are shocks doing that's different? All right. So here on the left, I have the famous supernova Reville Cassiopeia A. So it's a supernova. It's a few hundred years old, around in the 17th century, exploded. And so just zooming in here on a small section of the external shock. So I've got an exploded star, drives the shock wave into the interstellar medium. And then here is let's say a zealous graphics expert drawing particle trajectories on top of this, not much different than mine. And you can see particles effectively scattering back and forth across the shock and gaining the energy. Right? So I'll try to explain a bit more about what's going on, the mathematics, and what are the inferences of this. Okay? So this theory was developed in the late 70s independently by four different groups. The key point here is that at a shock front, you have a very narrow transition in the bulk properties of the plasma, so the velocity, the density, the temperature. If particles are energetic enough that they can sample back and forth across these shocks, in principle, they always see head-on collisions. That's basically the key point. And this was something that was already noted by Fermi back in the late 40s. And he considered, in fact, two galactic spiral arms converging would get a first-order mechanism. That was the last paper he wrote before he passed. Again, we want to exploit the isotropy, which requires U over V to be a small number. So again, we need some process to get the particles up to very high energy. But this kind of happens naturally at shock waves, because the shock transition itself is a very violent structure, particularly if the shocks are very fast. So there's many mechanisms to produce very energetic particles already in the shock transition layer, and then they can get up to the energies where they can really start scattering back and forth. Okay, so let's go back to how this would appear in our Fermi picture. Right, so all of our clouds are now nicely moving head on. So there's a frame in which they're always converging. This is not the shock rest frame. The shock has to be moving in this frame, but the particle in principle is just scattering off these converging flows. Okay, so they're always head on. And again, we assume that these collisions are so frequent that the distribution stays. All right. Is hopefully that's clear to everyone, right? So the way that you can think of this is imagine that if you are an observer that's sitting in the upstream, you see the shock, but also everything downstream of the shock moving towards you. So if you can go into the downstream and back, it must have been a head-on collision. But if you are a surfer sitting on the ejecta, so you're inside the supernova remnant, moving with the flow, you actually see the external universe moving towards you. So if you can get outside of the shock and come back, again, it's been a head-on collision. Okay, so it's always gaining energy. Okay, so we can have a look a little bit at the mathematics of this. So what's happening? So we have a particle. Let's consider a particle going from upstream. So the flow is coming in here in the shock frame. The flow is coming in at some few thousand kilometers per second, and it's going out at some fraction of that. Okay. So we consider a particle that's in the upstream, crosses the shock, does its thing in the downstream, and then comes back. Okay. So its energy would be conserved in the upstream. It would cross into the shock. You would do a Lorentz transformation into the downstream, does its thing, comes back. Energy is conserved while it's here. Comes to here, you do a Lorentz transformation back into the upstream, and work out what was the next change in energy. And it turns out, or the change in momentum is basically delta U over V times the difference in these pitch angles. This, I hope, looks familiar. In the Fermi case, for a head-on collision, for the 1D case we considered, mu was 1, and mu prime was -1, and so we would have gotten twice delta U over V. So we can continue this and try to work this out for a very large number of particles if we want to work out the spectrum. This is completely impractical. So what we're going to do is exploit this idea that you're isotropic. You've got many collisions, and you stay isotropic in the local fluid frame. Okay. So what is the average? Well, the average energy gain, we want to average in some way over that, taking into account that particles crossing from this side are basically only moving in one hemisphere, and particles that are crossing from this side to this side are only moving in the other hemisphere. So we scale them according to their anisotropy, so the flux, which goes as mu or mu prime, and we integrate all the right-going particles from 0 to 1, so all the particles going this way, and all the particles going the other way, -1. And if you do this integral, you find that the average change in fractional change in the momentum per cycle, so upstream, downstream, back to upstream, is 4 delta U over 3V. Okay, so note this is first order in U over V. Hence we call it a first order Fermi acceleration mechanism. Okay, and so we know how the energy is changing, or the momentum is changing. So the question is, does it also produce power laws? And the answer will, of course, be yes. Recall that the differential density, okay, it's just this number here. So n is 4 pi p squared df, or rather here. So 4 pi p squared f. We can now try to work out what is the escape probability from this system. Okay, so to repeat what we did before. So the flux across the shock from upstream to downstream. So we integrate over the right-going hemisphere. We ignore the gyro phase, so we assume it's reasonably isotropic, and so we can integrate over the gyro phase, and then we have this weighting factor which tells you the flux across the shock, and this is basically NB over 4, right? The U1 cancels out 0 to 1, or is much smaller than this rather, and so to leading order, this is NB over 4. So that's the flux of particles from upstream to downstream. While if we take a boundary, so take an imaginary boundary that's sitting a little bit downstream of the shock, and ask ourselves, well, what's the flux across this boundary? And so here, there's particles moving in both directions, but the net flux is, so we integrate from -1 to +1 to get the average across that boundary. And this is effectively just NU2. So they're just being advected away with the flow in the downstream. And so we can work out an escape probability because that's simply the flux to downstream infinity divided by the flux across the shock. And this gives us this expression here for the escape probability. And unlike in the case of second order Fermi, we see here that this is completely independent of momentum. So it doesn't depend on momentum, the escape probability. And it's a very small number, right? There's a very small chance of escaping. There's a much higher probability that you will interact with the shock many, many times. Okay, so how does this produce power laws? We do exactly the same game that we did with the second order Fermi case. So Fermi's picture. So we have the number above a certain momentum is simply those that haven't escaped. We do the same game and solve these equations, and we now have expressions for P escape, which was this. Sorry, we have this expression for P escape is 4u2 over v, and we have delta P over P, which was 4 delta U over 3P. And so we take the ratio of those, and we get a simple expression here, which depends only on one single parameter. Yeah? This number here, the ratio of the upstream to the downstream velocity. This is what's called the compression ratio of the shock. And this is let's say, the most powerful and elegant result of the entire theory. You produce a power law which depends only on a single parameter. And so what should that parameter be? Well, for those of you who know a little bit of hydrodynamics, we know that if you take the limit of a strong shock for a monatomic gas with adiabatic index 5/3, this compression ratio tends to 4. So if we plug that number in there, we get the number above a certain momentum is p to the -1, or the differential density is p to the -2. For relativistic particles, e to the -2. And so compare this to the cosmic ray spectrum, is -2.7. So we're close. Yeah, it seems to be sort of fitting together. Okay. So is there any questions up to that point? Okay, everything is clear. Okay, I mean, it's a very simple idea. You just have the idea of bouncing off clouds, and in the case of a shock, the clouds just happen to be facing one another, so always head on. Okay, so our key takeaway points is that shocks, again, what they are, abrupt transitions in the gas properties, so density, velocity. They're found in countless astrophysical systems, and we know that these systems are often associated with non-thermal emission. These shocks naturally produce power laws in the particle spectrum, and in fact, they must, right? Within this simple picture, they have to. If anyone can guess why that has to be the case. So what it's doing is, so if you ask yourself, why would you not produce a power law? The thing about power laws is that there's no intrinsic scale. Okay? And so in this process where we just have particles randomly bouncing off, staying close to isotropy, bouncing back and forth across the shock, there's no intrinsic momentum scale in this problem. It has to produce a power law. Otherwise, it would say that the particles know something about a physical scale. There is no physical scale in this system. Okay, so this is why shocks are so effective at producing power laws. The energy gain is first order, so we call it first order Fermi acceleration, or in the non-relativistic case, it's called diffusive shock acceleration. And again, the key prediction is that it produces this power law, which depends only on a single parameter. So we can either determine in terms of the NDE, so number of particles, or in terms of the space-based density, where it's changed by a factor of 2. And the power law shape is independent of scattering. Again, it only depends on a single parameter. Okay. So maybe it might be useful to see it in action. Okay, so here is a simulation on the left of particle acceleration taking place. So we inject particles at low energies at the position of the shock, which is located here, and then we'll watch the entire system evolve in time. Okay, so we start to inject at the shock, particle spectrum builds up, and what you see eventually emerging is it approaches the theoretical value, this p to the -4, e to the -2, and the distribution at a given momentum relaxes towards this distribution here, where you have an exponential fall off in the upstream, and it asymptotes towards a flat distribution in the downstream. Okay, this you can understand also very, very intuitively. The exponential scale height here is in the frame of the shock. particles are trying to run away from the shock. They're trying to diffuse, they're scattering, zipping out of the shock, but all the flow, the bulk flow is coming back in. And so what you have in the upstream is a balance between advection and diffusion. And in the downstream, you imagine most of the particles are simply just being advected away, and some of them are diffusing back towards the shock, which tends to smooth everything out. Okay? So here, because there's no competition, the diffusion smears everything out, it gets straightened out, and then here you have this competition between trying to get ahead and step back, and so you get this exponential fall off. Okay, and the other point is that the maximum energy just simply marches forward in time. We could put that in mathematical terms. So what we have is simply an advection problem balanced with a diffusion problem. And we can solve this equation here. It has two solutions, either a constant or an exponential scale height, or an exponential rather solution. And that's what you see is falling off exponentially in the upstream, constant in the downstream. This value here, L, so that's the scale height at which it's doing this. This depends on the diffusion coefficient, which we hadn't mentioned up to now. So the diffusion coefficient encompasses all of the details of the scattering. And so it's basically where a lot of the effort, theoretical effort, is put into working out what that number should be. We can work out roughly, the scale height is, again, this balance of diffusion and advection, so d over u. The residence time in the upstream, so the particle before it goes upstream does its little random walk and comes back, it's going to be of order L over V, so L the scale height divided by the velocity, which has this form. And this allows us to work out an acceleration rate, or an acceleration time, which we can simply define as P over P dot, which is a cycle time divided by the fractional energy change. This we know, and this we'll assume is of order, spends roughly the same time upstream and downstream. And we see that its scale is d over u squared. So this makes sense. Very fast shocks have a larger jump, so they accelerate faster. So large u, large velocity, short acceleration time. Small d, you're confined very close to the shock, so you cross many times. More cycles, short acceleration. Okay. What is the maximum energy, right? So this is the other big question. So for shock acceleration, what is the maximum energy? So we showed this is more or less our acceleration time. And if you do a more detailed mathematical analysis, you get a slightly different number. So you just get a numerical factor in front. So what determines the maximum energy? So until now, we've avoided discussing the form of D, but generally speaking, it takes this form, at least for the case of diffusion, along the magnetic field. Okay? So we'll use this as a proxy for what we're interested in. And so if we take the value, again, inferred from satellite measurements for the diffusion coefficient in the interstellar medium, this number is about 10 to the 28, again, with this energy scaling to the 1/3 power. Okay? So if you plug that number in here for a typical supernova remnant, so shock velocity might be 5 kilometers per second, like this. The diffusion coefficient was 10 to the 28. It would take you several thousand years to accelerate equal to GeV. Okay? That's what the energies where you're producing, for example, most of the radio emission, and we see radio emission from all supernova remnants, or from most of them, particularly the young ones that are much younger than 1,000 years. Okay? So interstellar medium turbulence is not enough to accelerate particles to high energies. Okay? So what you need is somehow or other to produce or to reduce this value, and you do this by the cosmic rays. They do it themselves. As you're accelerating particles, they'll also excite plasma instabilities, and this, in principle, reduces us to much smaller values of diffusion coefficient. And this is why I said at the beginning, we typically scale this mean free path or the scattering rate in terms of the gyro frequency. And if we take the absolute limit, when we set that value, the Hall parameter equal to unity, we get this value here, what's called the Bohm limit, which scales then as the energy, but it's much lower. So it's much lower than this value. You can plug in those numbers. So the maximum energy then is going to be a competition between this acceleration and other possible timescales. So, for example, the age of the system, you've only been accelerating so long, or there might be losses. Okay, so talk more about losses in tomorrow's lecture, but for now, I'm just going to focus on comparing the acceleration time with the systems age, okay, which gives a nice expression for the maximum energy. Okay, so here we follow the work by Lagage and Cesarski. So it's a very simple argument. What is the most optimistic result from supernova remnants acceleration or acceleration in any shock system? You can apply it elsewhere. Okay, so we just take our expression for the diffusion coefficient, we take our expression for the acceleration time, and we plug it in, and we find that the simple expression, the mean free path, has this form here. And then if we take the most optimistic scenario, basically the mean free path is the gyro radius. So again, the limit of magnetized transport. And we set the acceleration time equal to the system A. So you've been accelerating since the system was created. Then we can simply solve this, and we get, again, the gyro radius is about U shock over C times R, which is exactly the same as what we saw for the Hillis limit, with a small numerical factor in front. Okay, so it turns out that diffusive shock acceleration, if you take the most optimistic assumption about the scattering, reproduces the theoretical, or gets very, very close to the theoretical maximum that it can possibly achieve, right? The Hillis limit. The Hillis limit doesn't care about the physical process. It just says this is the maximum energy that you can realistically expect to achieve in a source. Okay, so we plug those numbers in. So take a typical, again, supernova shock, a few thousand kilometers per second. Interstellar magnetic field is a few microgauss, and the system might be a few parsecs. Okay, we plug those numbers in, we get, again, 10 to the 14 electron volts. And this is always a problem for cosmic ray physicists because it's a little bit too small for comfort. So the key thing here is that DSA, adopting the most optimistic conditions, can achieve the theoretical maximum. And the question is, of course, does it? Well, actually, this number seems to agree quite well with observations. If we take these numbers here and apply to these supernova remnants, we take 10% of this, we what you're producing gamma rays, and it would seem to fit quite well with the observations. Okay, so this sort of is promising, but cosmic ray physicists, as you probably have heard, are obsessed with this number, this Pevotron concept, and we want to accelerate particles up to 10 to the 15 electron volts, because this is the first feature in the cosmic ray spectrum. So here's where the puzzle arrives. Okay, so supernova remnants, they're not cooperating with the theory. If we take one of the big breakthroughs of the last 20 years or so, was the discovery of these sharp rims around the outside, which showed that the magnetic fields are very, very large. Right? They're not 3 microgauss, they're 100 microgauss or several hundred microgauss. And if I plug these numbers in here, I get well above 10 to the 15 electron volts. And then I should be producing all of these very hard gamma ray spectra extending up to much higher energies. But we don't. Okay, and so the question is, I don't know if this still resonates with the youth, but what's going on? All right. So here's where the plasma physics starts. Okay, so our shock is over here, off the page. If I had no scattering at all, particles would just escape to infinity. But in doing so, they generate a current. Okay, so you produce an electric current, and then the electric current produces a Lorentz force on a gas. You know, this is just standard MHD. So we can work out a displacement of a field line or displacement of gas, basically just by the Lorentz force produced by this escaping current. And this could perturb in a given time t. It can perturb field lines by some distance. Okay, so it's JB over rho c. Okay, if we want to produce Bohm diffusion, right? So then we really need to have the field disorganized on the scale of the gyro radius. That's effectively what Bohm diffusion is. So the mean free path is equal to the gyro radius because it forgets where it's going in one gyro radius because the field is so disorganized on that scale. All right, so here's my particle in this rather than that. Okay, so we can do a neat little calculation here. So I can work out the energy flux. So that's just the cosmic ray current times the given energy. So again, at the, more or less the highest energies. So this is an energy flux. This is the total energy, the rate at which you're per unit area that you're processing at the shock. And so clearly this number can't exceed this, so we have some efficiency parameter eta. And so if I set this delta S equal to the gyro radius, which is what is exactly here, and I substitute this J for this J here, I can solve this, and I get something that looks remarkably familiar. It's basically the Hillis or the Lagarde-Cesarski limit, certainly if I take the efficiency to be of this order. So this doesn't solve the problem at all. Okay. There is another way. Okay, and this is what we think is happening, and there's growing observational evidence that this in fact does occur. So on scales that are much less than the cosmic ray gyro radius, cosmic rays are very rigid, right? They don't care. Small scale fields, they average out over my gyro radius. So I produce this very, very large current, and then this drives the growth of fluctuations very rapidly on small scales. There's nothing to stop it. Okay, so I can do these simulations. I can take a little small simulation box. Here it's propagating towards the shock, and I can solve the MHD equations with some current passing through this box. And what I see is quite interesting. I start off with just small scale junk. It starts to build out some well-known modes at, again, what we can predict analytically. And then once they kind of get large, they explode. They grow very rapidly to large scales. So this is a very different type of structure and a very different type of physical process than what I showed on the previous slide. So rather than displacing field lines, you're really just mixing things up and allowing it to blow up. Okay, and so this is the key idea. When the energy becomes very large in the magnetic field, it grows to larger and larger scales, and this is what we think confines the particles. Okay, it stops them from getting out. And you can play around with the numbers and expressions for the analytic expressions, and you can work out an expression for the maximum energy, which at first sight doesn't look so good. If we take a typical supernova remnant a few hundred years old, these numbers, this is the efficiency, should be on the order of about 10%. And then we see, oh, we're still in the same issue. We don't get very high. But there's a very strong scaling here, and there's this density parameter here. So if we go to very young supernova remnants, this number can be made small, but this can be much larger. Okay, this could be 10 or 20,000 kilometers per second, maybe in the first few years. And this could be very high. You could be going into a very dense environment around the star. And in principle, if you plug in the numbers, this seems to be just about capable of getting up beyond a PV for favorable conditions. Okay, so my key takeaway points are the acceleration time is given by a nice simple expression, which again scales as u over v squared. So it is not correct to say, people often say that first order Fermi is because acceleration time scales as u over v. It doesn't, it's because u over v squared. The reason that it's u over v squared is because the particle spends a large part of its lifetime doing this little random walk away from the shock. It's only on that average over that cycle that it's first order. The maximum energy that you get is very close to the Hillis limit. If scattering is close to the magnetized limit or so-called Bolden limit, the scattering should be mediated by self-generated fluctuation. This is where the plasma physics comes in. You take the escape rays, they drive a current, they amplify magnetic fields. To accelerate the PV energies, we need strong magnetic field amplification, and what seems to be the limiting factor is the ability to confine particles close to the shock. Okay. And so this requires acceleration to be very efficient. Left. Ah, excellent. Okay. Okay, so let's just one last topic to sort of gloss on. So now everything I did up to now was pretty textbook stuff, apart from the last bit on the maximum energy. This is still something that's ongoing research, and of course, really need more and more observations to validate. So this is exciting times at the moment, and with the instruments like CTA and SWGO and LASSO, we're really revolutionizing this field. So there was one shortcoming of what I've said up to now. Um, we said that shock acceleration can only produce effectively one number. So we get a power law. The power law only depends on the compression ratio of the shock. And this compression ratio tends to have, for strong shocks, a rather universal value of 4. And therefore, I should always produce an e to the minus 2 spectrum. So this gamma here should always be 2. And then this alpha here, which is the associated synchrotron flux, for example, if I have electrons with an e to the minus 2 spectrum, then I should produce a synchrotron flux with 2 minus 1 over 2, which is a half, right? So I should get this number here to be a half. And so when people see numbers that are different from a half, they say, haha, it's not shock acceleration. Shock acceleration doesn't work because there's this one thing. Or they say, it depends on the compression ratio. So maybe the compression ratio is a little bit different. And so if I see a very steep spectrum, I must have a small compression ratio, and therefore it has to be a very slow, weak shock. The problem is that doesn't always work, and in fact, it's slightly counterintuitive. In fact, if you go to larger shock velocities, so these are where radio measurements are possible. So these are all these data points are different supernova remnants. As we go to larger and larger shock velocities, we see that the spectrum gets steeper and steeper. Okay. So the bulk are falling at this half, but we see many other options are possible, and there seems to be this trend. Okay. So we should possibly consider what are the different possibilities for deviating from this standard result. Okay, so one thing is we had a very simplified picture of what was happening. Everything we did up to now, we said simple shock, flow comes in, flow goes out. But if we need to produce 10 to the 40 ergs per second to maintain a steady cosmic ray spectrum. And so in order to do that, you need to take the rate of supernova remnants, which is, if supernova remnants are the source of cosmic rays, of course, about 3 per century. And if you take each supernova is about 10 to the 51 ergs. We take that number and we take that rate and we work out the total power. It's about 10 to the 42 ergs per second, averaged over the century. So if we want to produce or maintain a steady spectrum, we need to get about 10% of that energy has to be going into production of cosmic rays. So cosmic ray acceleration should be efficient. And a lot of evidence points to the fact that it is very efficient. Okay? And therefore, this pressure gradient or this gradient of the upstream that I showed you earlier, in principle can do work on the incoming plasma. So the incoming medium comes in, it sees this pressure gradient, which it's coupled to, and it basically slows it down. And so what happens is the overall compression that's sampled between here and here becomes larger, and this can become quite weak. Okay, so you can get a slightly smaller compression ratio at the shock. And so what this can do is now we've introduced a scale. Okay, and so there is a scale, and now you don't necessarily get a perfect power law, but you can get a concave spectrum. Very high energy particles have a long sampling rate, so they have a long mean free path, so they can go for all the way up here and back. So they see a much larger compression ratio, so they actually get a harder spectrum, harder than e to the minus 2. Low energy particles basically are stuck down here, scattered back and forth, and if that shock is weak, has a compression ratio less than 4, which it can, needs to be very efficient and can't have too high a Mach number to begin with, then in principle you can get a steepening of the spectrum. And so maybe this can account for what's happening. This is what we call nonlinear diffusion shock acceleration. And there's some tentative evidence that these type of processes are happening, but it's not at all conclusive. So another more interesting, to my mind, process is the possibility for non-diffusive behavior. So everything said up to now was very simple, one-dimensional diffusion, particles just doing random walks. But if you actually take detailed field topologies, magnetic field topologies, particles don't really diffuse. They do on very, very long timescales, but on short timescales, they can have a memory. And so I'll just highlight some examples here. So here's turbulent magnetic field, just a simple two-dimensional geometry. And you look at these are particles that are released on a layer. Okay, and you can start to see all sorts of phenomena. You see particles just get stuck in these little sort of low magnetic field points. These ones here tend to just follow, they go along between regions of strong and weak magnetic fields. So they're kind of like birds going through swamps and just finding these nice little roots. Okay, so the distribution doesn't have to be diffusive. And this has an important fact, because the fact that we got this e to the minus 2 spectrum was exactly because we had the flat spectrum in the downstream. Yeah? So we just had this constant rate of escape. The distribution at the shock is slightly different from the distribution far downstream. Then you have enhanced escape probabilities, so or reduced escape probabilities, right? So the ratio of the flux escaping across my boundary at far downstream mightn't necessarily be the same as what's at the shock, and therefore you can produce slightly steeper or slightly harder spectrum. That's what we call sub or super diffusion. And the other possibility, and I didn't mention this at all because it just opens up a huge can of worms, was shock obliquity. So everything I showed you up to now was really a singular case. It was a parallel shock with very, very small U of V. Okay, so if I have a parallel shock here, cosine theta is the angle between the magnetic field direction of the shock propagation. If it's very, very small, so if they're exactly aligned, then everything I showed you is reasonably okay, modulo these effects. But as I deviate from that, other interesting phenomena starts to happen. So there starts to be the possibility of enhanced acceleration because particles are stuck close to the field. And as I go to highly oblique shocks, particles find it very difficult. It's easy to go along a field. It's difficult to go across a field. And if it's difficult to go across a field, all my particles are trapped, and I get very, very steep spectrum. So here, this is the spectral index. So p to the minus 4. Here we are p to the minus 6, let's say, for a perpendicular shock. Okay, so there are many ways, many complexities which can be added to this shock acceleration picture, which might add more information to the global picture. All right. So to conclude, I think we have a nice, or let's say it's a personal picture of what's happening for galactic cosmic rays and their origins. I very much am in favor of the idea that the vast majority of these particles here are produced in supernova remnants, again, up to more or less the knee. The highest energies are achieved in very young, fast supernova remnants in dense environments, because that's the right environment in which to get this strong magnetic field amplification, which you can exploit. It's easy to get large magnetic fields. It's not easy to get them to really influence the highest energy particles. Above the knee, which I didn't really talk about, here we need I think, another class of accelerator. And so possibilities include microquasars, massive stellar clusters, or there may be something in the galactic center, something which we don't know. We certainly know that there's a very hard gamma ray spectrum associated with the galactic center, and it's becoming quite clear that massive stellar clusters also appear to have quite hard spectra extending up to the current limits of what we can see with Cherenkov telescopes. So it's clear that there are particles being accelerated to very high energies there. We just need to develop a detailed understanding and improved observations. The energies above the ankle, I think, remain very much a puzzle. So the experiments like Pierre Auger, TA telescope array in the north, are instrumental in this. But of course, we need to really ask ourselves the question: how does nature produce 10 to the 20 electron volts? It's a huge amount of energy, and there's very few physical processes that can actually do that. And I think the key conclusion here is that confirmation of all of this is just a theory, right? And theory is nothing until well, theories can always be disproved. You only confirm your biases, but confirmation, let's say, in some way requires multi-messenger detections. And this really falls in the regime of gamma ray observations and neutrino measurements. Okay, so that's more or less where I thought would be a good place to stop. So what I want to do in the next lecture is talk about alternative acceleration methods, really focus on relativistic shocks, because these turn out to be, as Alicia said, the largest population of galactic gamma ray sources are coming from pulsars, where we think it's relative shocks, and sort of tried to connect what's happening from we have a source distribution of power laws, of energetic particles, what are the associated emission processes and cooling that play a role there, and then the associated non-thermal emission spectra. So I think that's probably a good place to stop. Thank you.
Okay, questions?
Yeah, thanks. It was a wonderful lecture. So I have a couple of questions. So can you please go to the initial slides where you have mentioned about the cosmic ray density? I think slide number 5. So like my question is like you mentioned about the density in the local galaxy. If you talk about our own galaxy Milky Way, so how many events occur per unit time to maintain this galaxy, like this density in our galaxy? And what are the likely candidates to maintain this galaxy or maintain this density in our galaxy?
The energy density in
Yeah,
the cosmic ray. So this was, yeah, okay, so that was the point I was making just there at the end. Maybe it was a bit rambly. Okay, so this is the cosmic ray luminosity. So this is the cosmic rays escaping our galaxy. And
yeah.
so if we need a steady state, then power out must equal power in. Okay, so we need something that's producing roughly 10 to the 40 ergs per second, averaged over this time. Yeah. And so there's very few sources that can do that. And so the one which probably is most favorable is supernova remnants. So accumulated over, if there's 3 per century, that's, you can work out then the total, and each one releases 10 to the 51 ergs. 3 per century, the rate is about 10 to the 42 ergs per second.
Okay.
Is basically the rate at which power has been produced by supernova remnants. That's total kinetic energy of the supernova remnants. And so we need an efficient process that taps into about 10% of that to account for this energy.
Okay. So I have another question. Maybe it's silly question. So I just want to know: is there any scenario in which the both Fermi acceleration mechanism work together to accelerate the particle?
Yes, right. So interestingly, the two processes are the only difference between the two processes, the timescales. So it's sometimes, this is why I was highlighting this misnomer when people say it's a second order effect, because the acceleration times both go as u over c squared, effectively, for relativistic particles.
Yes.
So both processes have an acceleration time which goes u over c squared, but the u for second order Fermi, so for the classic second order Fermi acceleration, this u is the velocity of the scatterers. The shock, by definition, a shock is moving faster than any scatterer. Otherwise, a shock can't form because information can propagate ahead and say, "Hey, something's coming. don't shock." So, so it's always faster. But if you have a very low Mach number shock, so if it's a Mach of a few, then the two numbers can become comparable, and then it's competitive. And so this has been used to account for some of these composite remnants or these field remnants that you would have. Okay, you have an accelerator which is localized at the external shock, and then the downstream is very turbulent, and then you have second order Fermi which sustains that, and in principle can in fact lead to hardening of the spectrum. So that's why you see some of those filled supernova remnants have very hard spectra. It's because second order Fermi is operating there.
Yeah. Okay. Thank you.
More questions?
Was it too easy or too hard?
Hi. I'm just a bit confused. I think what's the relation of the Hillis limit with the Fermi acceleration? Because the Hillis limit is always valid, yes?
Hillis limit is a limit, yes.
Yes, it's always there.
Mhm.
And we use then the Fermi acceleration as the mechanism that we think actually accelerate the particles. And we hope that in the maximum range of the Fermi acceleration will be limited by the Hillis limit. Yes.
Yes.
Okay. But then that 10 to the 14, it means like the Hillis limit for the NR.
Right. So a
That,
big,
yeah.
yeah, maybe I can elaborate a little bit. So the thing is, the Hillis limit is just a number, right? Where were we? Too many slides. Okay. And cartoons I can't skip. Okay. Right. So the Hillis limit gives you this. Yeah. And so you need to choose. So Hillis limit is agnostic to the acceleration process. So you need to choose values to put in here. Okay. And so I would say I can make observations. So I make an observation of a supernova remnant, say, and I say, okay, I know how fast the shock is moving. It's moving at 4,000, 5,000 kilometers per second. So that's the number I'm going to use there. The size of the system, I can infer if I know the distance, angular, so I know what this is. Now, the magnetic field, this is always the tricky part, right? So we infer from the observations, from X-ray observations, and for Cas-A, for example, we have a lower limit, right? Because I can explain a bit more about this tomorrow. So for Cas-A, you can exploit the fact of the inverse compton, the gamma ray and the Bremsstrahlung emission, and that sets a lower limit on the magnetic field, which has to be above 100 microgauss. And that number is large. Now, that just tells you the potential, okay? It doesn't tell you that you're going to get it, that you're really going to sample that full electric field, okay? What then the connection with shock acceleration is really saying, okay, I now have a prediction for the rate of acceleration, but I don't know what my diffusion coefficient is. And so I'm going to be the most optimistic I can be. And then that, in principle, produces something that's very, very close to that. It doesn't have to be that, yeah. And in reality, it falls well short of it from the observations of, I mean, if I try to compare the prediction for this with 100 microgauss with my maximum energy, and then I look at gamma rays. So again, I take Cas-A, my maximum energy should be almost, I mean, several tens of peta electron volts. I look at where the cutoff in the gamma ray spectrum is, it's like 100 TeV. It's really, really low. It's 10 TeV for Cas-A. It's surprisingly small cutoff. So then there's this contradiction. So why is it not the most efficient accelerator it can be? So Hillis tells me it should be this maximum energy, but the physical process that's trying to tap into this energy just falls short. And the reason that I think that's happening is that the fields, this B, is concentrated on really, really small scales. So it's concentrated on small scales that just average out for the particles that's gyrating around. So it doesn't see that electric field. That electric field, it just averages out, it doesn't care. And so it's seeing a larger electric field, which is much smoother, and therefore you just get to a lower maximum energy.
Okay, thank you.
Yeah.
So the part spectrum that you have shown is a superposition of everything there is in the galaxy, probably because you don't know the arrival direction, right?
Mm-hmm.
So you have argued that this part law can be just from supernova remnants. Can you do you have an estimate, because of the number of supernova remnants and so on, of the normalization? Can you reproduce a normalization of the part spectrum?
So it's, if you take all gamma ray observations where we can actually then make a measurement, there is a slight tension, but this is, again, this was really done with the Hess galactic plane survey. So they took all supernova remnants that they could see. They tried to work out what would be, assuming it was a hadronic emission, what would this give you in terms of normalization. There's a big uncertainty in terms of the target density. Yeah, so to actually infer cosmic ray energy density from a gamma ray spectrum there's a large error in that, a large uncertainty. And of course, then we need to extrapolate, because most of the energy is sitting here at a G. And of course, then you need an instrument that's really seeing the turnover, right, in at a few of 100 MeV. So if you take all the Hess measurements, then you extrapolate those to lower energies, it seems to be like almost in tension, but then there's plenty of wiggle room for the gas density. So the cosmic rays could just be sitting in low density regions, and therefore they're not bright. So really, the argument is purely an energetic one. This is basically the leading argument, has always been that way. I mean, this dates back to the 1950s, even before we knew anything about the acceleration mechanism. Ginsburg famously just did this simple energy argument and said, well, supernova remnants is probably the only game in town. There was a question here. Oh.
So thanks for talk. And I want to, in any moment we specify the nature of the particle, right? I thought maybe the probability of the particle go to the clouds would change if it was a boson or a fermion, and this doesn't make any difference.
To lowest order, no. For what I did here, obviously, when you start talking about electrons, then cooling becomes an issue you have to worry about. It's very rare that you have to worry about cooling for protons, because the cooling rate for PP interactions is very, very low. But I'll talk more about that tomorrow, because then you need to, there's lots of interesting physics then when you start looking at acceleration of electrons, because you can get rather extreme environments, and then you have to worry about quantum corrections and Klein-Machine effects. So it's a lot of interesting, rich physics there, which seem to match nicely with observations.
Thank you for the lecture. I was just wondering about you said that for the calculation of the Hiller's limit, you did not consider the work by the magnetic field, because it vanished in the equation. But if you consider the annihilation of the magnetic fields, the magnetic reconnection, and the increase of the energy due to the transformation of magnetic energy into kinetic energy, this could increase the Hiller's limit for the supernovas, or the magnetic reconnection in this shock front is not, it's negligible.
Right. So obviously, if you have annihilating fields, you have a dBdt, and we know from Maxwell's equations a dBdt must have a curl of E, and so therefore there is then an electric field associated to that annihilation. It's my general, and I mean this is a personal bias. Magnetic reconnection is a kinetic process. It really is happening down on small scales, where you're down basically where resistivity or anomalous resistivity is coming into play. And again, for the similar arguments to this nice lady's question, I think when you're really talking about the highest energy particles, most of those fields effectively cancel out. So you can only tap into them to a certain energy. I think magnetic reconnection is probably an important part to play in initial energization processes in many cases. And there are certainly cases where it's going to be very effective in relativistic systems. Supernova remnants, I think it's really a perturbation. It's not going to be a dominant effect. I'm happy to be proved wrong, but I mean, you would really need to explain how you can contain so much energy wound up in basically that the total electric field you can release due to just topological deformations of the magnetic field can really produce the accelerating potential that you need.